there's something. Hello.
Yeah.
Okay. Welcome to the quantum symmetry seminar. Today, we are very happy to invite Professor Hong Li from Harbin Institute of Technology.
Okay.
He is going to give us this talk. The title is Quantum Holomorphic Evaluation and the Universal Property of Complex Simple Quantum Groups. Let's welcome.
Very much. It's a tremendous privilege for me to share my research with the researchers here in BIMSA. And this is my second time to be here. And I really enjoy these great facilities and nice city of Beijing. And thank you for this kind introduction. And thank you for the invitation. Okay, today I'm going to talk about what Professor Wu just said. And let's begin. And this talk is based on this joint work with Christian Voigt from University of Glasgow, which is still in progress. And yeah, to gain some motivations about what I'm going to talk, let's first look at a brief history of Q deformations. Okay, so this was the first example of the Q deformed compact semisimple Lie group, namely SU2. And for this introduction of SUQ2, one first makes this simple observation on the algebra of continuous functions on the compact Lie group SU2. The C of SU2, which is very well understood from many different areas of mathematics, is isomorphic to the unitary universal system algebra generated by alpha and gamma, subject to the relations. So in standard presentation of SU2, one usually consider this kind of numbers such that this modulus is equal to 1. So alpha and gamma represent coordinate functions on this 1, 1 and 2, 1 matrix component. So they are elements inside the C of SU2. And using these two coordinate functions, one can very easily show that C of SU2 is given by this presentation in terms of generators and relations. Then Voronowicz came in 1987. He found a one-parameter deformation of this algebra of continuous functions. And for that, fix one number between 0 and 1. Then C of SUQ2 is defined as the unitary universal system algebra generated by two elements, alpha and gamma, satisfying these 5 relations. You see, they are just slight deformation of the relation satisfied by the coordinate functions of C of SU2. But an important observation is that now alpha gamma don't commute. Okay, so whereas in the commutative case, those two coordinate functions are of course commuting. But now we are in the non-commutative realm by requiring this, and the non-commutativity is controlled by this parameter Q. And the others can also be related like in a similar manner. So this is the T of SUQ2 is given by this generator and relations, generators and relations. And one key observation is that these one-parameter deformation gives us a family of non-commutative compact quantum groups. Okay, in this talk, I'm not going to talk much about quantum groups because we are going to focus only on system algebras underlying those quantum groups. But anyway, by means of this Q deformation, we have produced very interesting class of non-commutative system algebras. So that is the point. And now we want the Q deformation of the non-compact Lie group SL2C. But the situation is much harder here because the group itself is non-compact, and hence the machinery of system algebra needs to be dealt with more care than the compact case. So C naught SL2C, which is the algebra of continuous functions vanishing at infinity of this non-compact space SL2C, is a unique C-star algebra satisfying the following universal property. And this isn't the usual way that one understands this simple C-star algebra, but for the sake of comparison, or to give more motivations behind the Q-deformed SL2C, which I'm going to introduce in the next page, let's look at it step by step. So the universal property states that there are 4 unbounded elements, alpha, beta, gamma, delta, affiliated with C naught SL2C. Okay, I'm not going to give you the definition of unbounded affiliated elements, but suffice to say that they are kind of unbounded continuous functions, so that those concepts of unbounded elements affiliated with C naught SL2C are precisely given by elements of C of SL2C. Okay, so those continuous unbounded functions are precisely the unbounded elements affiliated with C naught SL2C. And this, even though we are going to look at more general C-star algebras, this will be the intuition behind this concept of unbounded elements affiliated with certain C-star algebra. Okay, so this unbounded affiliation will be denoted by this membership inside C of SL2C. So the universal property says that there are these 4 unbounded elements satisfying this relation, which states that those alpha, beta, gamma, delta, as well as their conjugates, all commute with each other, so that the resulting C-star algebra should be commutative and satisfy these 2 relations, which are satisfied by the standard coordinate functions of SL2C if we present SL2C by this, and you know the very usual procedure. So alpha, beta, gamma, delta are coordinate functions in the respective matrix entries, such that these unbounded elements satisfy this for any Hilbert space A, and operators, 4 operators in this algebra of bounded operators on the Hilbert space, satisfying the same relations as above, same relation, commutativity and unit determinant conditions. Satisfying the above relations, there exists a unique non-degenerate star homomorphism from C naught SL2C into this algebra of bounded operators on H, which extends to this bigger algebra of unbounded elements, and this extension sends this unbounded element alpha, beta, gamma, delta to this tilde of alpha, beta, gamma, delta. It's very complicated, and one doesn't need to conceive of this universal property when dealing with C naught SL2C. But this complicated universal property is very important because this gives us a smooth transition to Q deformations of SL2C. So this was introduced, the Q deformation of the Lorentz group, because this is called the Lorentz group in the literature, was introduced by Poders and Vornovich in 1990. Okay, so again, as in the SL2 case, we fix one parameter Q between 0 and 1. Then C naught SL2C is the non-unital unique C-star algebra satisfying the following universal property. Again, as in the SL2C case, we suppose the existence of 4 unbounded elements, alpha, beta, gamma, delta, affiliated with C naught SL2C. And again, we express this fact by this membership of the 4 elements in C of SL2C. But even though we don't know about the definition of it, it's an important fact that this becomes a star algebra, unitary star algebra. Okay, and then one requires that these 4 unbounded elements satisfy these 17 relations. Very, very complicated. But anyway, this was how it was introduced, such that these 4 unbounded elements satisfy an analogous existence property as in C naught SL2C. So after these 17 relations, the universal property just goes like this. So after this, universal property is the same. So given any Hilbert space and operators alpha, tilde, beta, tilde of alpha, beta, gamma, delta, satisfying these 17 relations we can always construct a star representation from C0 SAQ to C to L of A, which extends to this bigger algebra of unbounded elements, sending the four prefixed elements to the tildes of alpha, beta, gamma, delta. Okay, that was how it was introduced, but they further proceed to prove that this SAQ2C, which was defined as a universal zeta algebra satisfying that complicated universal property, is actually given by the minimal tensor product between C of SAQ2, which was already introduced by Voronowicz, and C star SAQ2, which is the discrete quantum group dual to C of SAQ2 provided by the general theory of locally compact quantum groups. So they are in duality. And if we take the minimal tensor product of these two C star algebras, then we get this. And this is a unique C star algebra satisfying that universal property. As a matter of fact, this theorem that I denoted as theorem is the definition taken in Podolsky and Voronowicz paper, and they proceeded to prove that this minimal tensor product C star algebra actually satisfies this universal property. But anyway, for the sake of the flow and the story of this talk, I just switched the two, and that's just a fact. But you can just take it as a theorem. Okay, I will going to refer to this as a theorem. Okay, so this Q deformation, these Q deformations were later generalized to arbitrary compact semisimple Lie group as well as arbitrary complex semisimple Lie group. Okay, not just SU2 and SL2C. Okay, so if we apply this general procedure called Q deformation, then we get a one-parameter family of non-commutative compact quantum groups. Non-commutative compact quantum groups, and we apply this Q deformation to this complex semisimple Lie groups, then we get non-commutative locally compact quantum group. And they form very interesting classes of quantum groups in the literature. So this procedure called Q deformation is a very, very interesting construction in the theory of C star algebras for sure. But the problem now comes here, because after this work of Podolsky and Voronowicz, the Q deformation of the complex semisimple group G has always been taken as the C star algebra given by this minimal tensor product between the C star algebra underlying KQ and its dual C star algebra. Okay, this has been taken as the definition, whereas I refer to this as a theorem. So the problem is this: where is the universal property? The universal property was the main motivation behind the introduction of the quantum Lorentz group. But after this work, the universal property has largely been lost in the literature. Okay, that is the gap that I'm going to address in this talk. But there are several difficulties in generalizing this universal property to more general complex semisimple Lie groups. Because first of all, what is the corresponding universal property when G isn't equal to SAQ2C? So SAQ2C is the simplest complex semisimple Lie group, and we know from where we can start, from where we can deform the universal property, because this admitted very simple presentation in terms of four coordinate maps, coordinate functions, and we deform the relations satisfied by these four coordinate functions in SL2C to obtain SLQ2C. But for more general complex semisimple Lie groups, it's not even clear where we should start out to get Q-deformed complex semisimple Lie groups. And also for exceptional Lie groups, there are not even any canonical coordinate descriptions of those Lie groups. Okay, so that was one difficulty to start out. And also, the other difficulty is that there would be far too many generalization relations for general complex semisimple Lie groups. Yeah, you already saw that. You already witnessed that for this simplest example, we already had 17 relations. Now you can imagine how many relations we would get if we just increase the length. For example, how many generalization relations we need for, let's say, Q to C and so on. And it wouldn't be very practical. So we stick to find the generator and relation free formulation of the universal property. And that's what I'm going to do. And that's what I generalized to arbitrary complex semisimple Legals. Okay, to do that, to find this coordinate-free description of the universal property, we need to look at algebras of polynomials on complex semisimple Legals. Okay, let's first look at the classical case of SL2C to gain some motivation. Okay, first, define this for SU2, the algebra of polynomials on SU2 as the start of algebra inside C of SU2 generated by this two coordinate function. Okay, and then it is a standard fact, in fact, an easy exercise to prove that this set of all star-preserving characters. Star-preserving characters means that we consider all or characters, non-trivial characters, which is star-preserving onto the set of complex, the field of complex numbers. They should be non-trivial. And then one can show that this is actually given by point evaluations at the point of SU2. Okay. This can be proved, for example, by Hilbert's Lorentz and on the right-hand side, we also have this from general theory of cis algebras, the theory of commutative cis algebras. We know that those star-preserving characters of this cis algebra C of SU2 are actually given by pointwise evaluation. So this relation establishes an interesting bridge between algebra on the left-hand side and analysis on the right-hand side. And further, let's look at another such phenomenon. So let's increase to the complexification SL2C. We define this polynomial algebra on SL2C as the start of algebra generated by the four coordinate function. Okay. Then one can also prove using the analogous methods such as Hilbert's Lorentz and also the standard cis algebra theory. One can show that those spectra of for SL2C and C0 SL2C are actually given by pointwise evaluations at the point of SL2C. Okay. And one fact is that, an important fact is that this polynomial algebra on SU2 is embedded into polynomial algebra on SL2C via this non-star preserving map. So if we just give up the star preserving property, then we get four generators for SU2, namely alpha, gamma, gamma star, and alpha star. Okay, and we send them to the corresponding generators in for SL2T. In matrix notation, this might be written as this. So we send the fundamental representation of SU2 to the fundamental representation of SL2T. Okay, so in a sense, this gives us extension of functions on SU2 to functions on SL2T. Okay, and those elements are actually holomorphic polynomials on the complex manifold SL2T because these coordinate maps are just holomorphic coordinate functions on SL2T. Okay, because they are holomorphic polynomials, now we can consider these images of those extended functions under the complex conjugation of for SL2C. This involution is just complex conjugation, and we denote the image of the embedded for SU2 inside for SL2C under the conjugation by Paul bar SU2. And then because we just have taken complex conjugation, then elements inside Paul bar SU2 are given by anti-holomorphic polynomials on SL2C. Okay, they are just elementary observations. But an important observation to be made is that algebras for the polynomial algebra on SL2C is actually isomorphic to the tensor product algebra of for SU2 and for SU2, the two copies of for SU2, such that under this identification, this first tensor component is mapped to holomorphic polynomials, whereas the second tensor component is mapped to anti-holomorphic polynomials. Okay. this is a basic fact that can be deduced from the very definition set. This was generated by the four holomorphic coordinate functions and their conjugates. And that's the involution, which is the complex conjugation interchanges the two tensor components. So a priori, the right-hand side is only an algebra, but the left-hand side is a star algebra. So we can pull back the involution on the left-hand side to the right-hand side. Then this involution becomes this, because if we take the complex conjugate of a holomorphic polynomial, then we get an anti-holomorphic polynomial, and vice versa. Okay, that's why this relation holds under the identification. Okay, then now everything is not very clear, but now we can generalize this polynomial algebras on arbitrary complex semisimple quantum groups, Q-deformed complex semisimple Lie groups. Okay. Yeah, I'm going to assume that the audience is familiar with this for KQ, this algebra matrix coefficient of KQ, because explaining this would just take us too far afield, because this requires a whole one full talk, I think. So let's just assume that there is a star algebra. This isn't the C-star algebra, but this is the star algebra representing the non-commutative space KQ. And for those of you who are familiar with the theory of complex quantum groups, this is the Hofstad algebra, namely the dense algebraic complex quantum group underlying KQ. Okay, let's denote the complexification of KQ by GQ. Then let's ask this question: what is the algebra of polynomials on GQ? We already looked at algebra of polynomials in the case of SL2C, but we want to generalize that to arbitrary complex semisimple Q-deformed complex semisimple Lie groups GQ. Then, inspired from the previous observations, as a vector space, we require that this algebra of polynomials on GQ should be given by the tensor product of Pol KQ and Pol KQ. We want two copies of Pol KQ inside Pol GQ. And Pol KQ tensor 1 and one tensor Pol KQ, the first and second tensor component, should be subalgebras of Pol GQ. We don't know about the algebra structure of Pol GQ yet, but at least we expect that this bigger polynomial algebra should reflect the algebra structures of Pol KQ. And this first tensor component represents holomorphic polynomials, and the second component should represent anti-holomorphic polynomials. That's the second requirement. And third requirement might be the most unintuitive at first sight, but this is very intuitive. Okay, the multiplication map. You see, by this definition of Pol GQ as Pol KQ tensor Pol KQ, we have the multiplication map of Pol KQ, which is just a priori, just a linear map of Pol KQ. Then we require that this multiplication map is algebra homomorphism. In fact, not just algebra homomorphism, but star homomorphism. We require that because classically, this multiplication map corresponds to the restriction map of the functions on GQ into KQ. Okay, what this means can be obtained from this. So originally, when we embedded Pol SU2 into Pol SL2C, we said that functions on SU2 are extended holomorphically to functions on SL2C, this bigger space SL2C. And the second component, for the second component, functions on this SU2 were extended to SL2C, this bigger space SL2C, anti-holomorphically. So if we extend the multiplication map, those holomorphic polynomials and anti-holomorphic polynomials, then we get are just functions on SU2, and this amounts to forgetting about holomorphicity and anti-holomorphicity, and we just consider their restrictions to smaller space SU2. Okay, of course, because all algebras appearing here are commutative, this map is star algebra homomorphism, and so this multiplication classically corresponded to the restriction map. And it's a general philosophy of the theory of system algebra that quantum analogs of restriction maps should be star homomorphism. Okay. In fact, subjective star homomorphism. But anyway, that is the intuition behind this requirement, that this multiplication map M of should be star homomorphism. Okay, that is the content of the third condition. And the fourth condition is that the involution must interchange the two tensor components by this formula. Okay, because this first tensor component represented the holomorphic polynomials, and the second tensor component represented anti-holomorphic polynomials. So that if we take the conjugation, then we should get anti-holomorphic and holomorphic respectively. They should be interchanged like this. And this formula was actually inspired from this Christian relation. Okay, then we see that there is a solution to these four requirements, and that was given by Hodges in 1997. And to give to you the definition, the solution given by Hodges, we need to look at more preliminaries on this Q-deformed complex semisimple Libres. So let small g denote the Lie algebra of G. Then we have this quantized universal enveloping algebra, the so-called Dirichlet-Jinbo Q deformation. This is the Lie algebra counterpart of the Q deformation that I introduced in the system algebra of functions part. Okay, this is a kind of dual construction. Then Dirichlet actually discovered this universal R matrix of UQ of G. But I'm not going to give you the definition of the universal R matrix of UQ of G. But suffice to say that this universal R matrix gives us a bilinear pairing between pole KQ given by this formula. Okay. So I think it is sufficient to understand this universal R matrix gives us a Q pairing given by this formula. And then Hodges proved that the algebra of polynomials on GQ, if we define pole of GQ as a so-called quantum double defined by this pairing, so if we have this Q pairing, then we can, there is a standard algebraic procedure to define the quantum double defined by the above this Q pairing. And this quantum double satisfies all the requirements, all the four requirements here. So the quantum double is as a vector space given by these tensor products. And also each tensor component is a subalgebra, and the multiplication map is a star homomorphism, and the involution interchanges the two components. Okay. Yeah, I've written down some multiplications behind multiplications on this algebra of polynomials, but it is sufficient to note that in the multiplication, the universal R matrices they appear in the algebraic structure of pole GQ. And a consequence is that if deformation parameter isn't equal to 1, then because these universal R matrices are non-trivial, pole GQ defined as the quantum double is non-commutative. Okay? And Hodges proved that pole GQ is a unique star algebra satisfying the above conditions about the four requirements about algebras of polynomial, the algebra of polynomials on GQ. And here is the most important observation that will be relevant for our talk, is that if we take GQ as SLQ to C, then this polynomial algebra defined as the quantum double is isomorphic to the star subalgebra of C of SLQ to C generated by alpha, beta, gamma, and delta. Okay. From this point, now we can reformulate the universal property of SLQ to C in terms of algebras and homomorphisms, okay, very succinctly. So to do that, let's briefly recap this universal property of SLQ to C. So we considered 4 unbounded generators satisfying these 17 relations. Yes.
I have a question.
Yes.
Something is Harbin.
Yes.
So the universal R matrix is unitive, right? Do you need that condition?
No. Yeah, to the best of my knowledge, it isn't unitary matrix.
Yeah, so you don't want the R matrix that you're using for the skew pair, which
yes.
you're using.
Yes.
Shouldn't be.
Yes.
Yeah.
Exactly.
Because otherwise, I think you get like the the usual thing, right? You have Q and then you have the functions.
Yes.
Yeah.
Yes.
But this is not like polar GQ. This guy is not the quantum double form by UQG and CQG.
No.
Okay.
Yeah, there are many quantum double constructions related to this, centered around this object called complex semisimple quantum group, but this is one particular quantum double.
Yeah, this is like another thing.
Yes.
Okay.
Thank you. Again, other questions? Okay. Thank you. Okay, so we just consider these 4 generators satisfying these relations, but now the strategy is very clear because we have found star subalgebra inside this star algebra of unbounded affiliated elements generated by these 4 generators. So now we can state this universal property in terms of algebras. Okay, those 4 generators and relations are subsumed into this algebra, okay, and relations. Okay, yeah, let's look at this reformulation of the universal property step by step. So the algebra C naught SLQ2C is a unique C algebra satisfying the following universal property. Okay, so yeah, to be strictly rigorous, to be absolutely rigorous, I needed to denote the universal C algebra by another symbol, and we need to prove the isomorphicity of the 2 C algebras. But for the sake of simplicity, I will just denote by the universal C algebra as C naught SLQ2C. Okay, so there is a star embedding of this polynomial algebra given by the quantum double into this algebra of unbounded affiliated elements, such that any unitary irreducible star representation pi from this polynomial algebra into this representation on Hilbert space gives rise to a unique non-degenerate star representation of C naught SLQ2C via this commutative diagram. So let's look at this step by step. So we start out from a irreducible star representation pi. Then, because this SLQ2C is actually given by generators and relations, this means that alpha, beta, gamma, delta are mapped into alpha, tilde, beta, delta, gamma, tilde, delta, tilde, satisfying the same relation. Okay, the same relation because pi is star preserving. Okay. So now we see that the very existence of this star representation of this polynomial algebra guarantees us the existence of the 4 bounded operators inside L of H satisfying the relation. And hence we can use the universal property of Poders and Voronich to find an extension of this representation into the bigger space C of SLQ2C, because in the universal property, we actually postulated the non-degenerate star representation extends to this bigger star algebra. And then this extension, because for SLQ2C is assumed to be embedded into SLQ2C, I'm going to talk more about this later. So this pi extends to this bigger algebra, and we restrict this star representation to this smaller algebra to get a non-degenerate star representation of C naught SLQ2C. Okay. So this is the content of the universal property, and the universal property was very succinctly summarized in this commutative diagram. Okay, so compare the complexity of the original universal property with this very succinct commutative diagram of the universal property. And what we did, here is the main result of our work. What we did is to generalize this reformulated universal property to arbitrary complex semisimple Lie. Okay, that was what we did. And here, let's follow the universal property step by step again. So the algebra C naught of GQ is the unique C algebra satisfying the following universal property. Okay, again, for GQ is defined as the quantum bubble, as in previous slide, and we postulate a star embedding of this quantum double into the algebra of unbounded affiliated elements to this algebra C naught of GQ, such that any unitary irreducible star representation from this polynomial algebra into the algebra of bounded operators gives rise to unique non-degenerate star representation of single object Q via this commutative diagram. So we start out from pi. Then, because from analogy, this must be given by some very many generators and very complicated relations, but they are all subsumed into this polynomial algebra. We don't need to talk about generators and relations anymore, but this existence of pi, this star irreducible representation, produces corresponding bounded operators in this L of H, satisfying very many generators and very complicated relations. Okay, just as in SLQ2C case. Then we prove that actually this star representation extends to this bigger unitary star algebra, unitary star representation of pi tilde, and we restricted this extended star homomorphism to this smaller algebra to get a non-degenerate star representation of C naught to Q. And we proved that this is actually unique, and this universal property characterizes this C naught of GQ. Okay, so this is the reformulation, I would say reincarnation of the universal property of SLQ2C, which was the original motivation behind the introduction of the concept of the whole concept of complex semisimple quantum groups, QD from complex semisimple liquid. Okay, so this itself is very satisfying, but another important consequence of this universal property is this. So this implies that this spectrum for GQ. Now we are dealing with non-commutative algebra, so we need to be careful. This isn't just a set of all star preserving characters. So in the commutative case, we could have just defined this like this, but because for GQ are non-commutative algebras, we need to consider infinite dimensional representation. So they are star irreducible representation. Okay, so this sets denote the set of all equivalent classes of irreducible star representations of the non-commutative star algebra for GQ and non-commutative C star algebra C naught GQ respectively. And yeah, if we follow this commutative diagram and if we look at the procedure, I cannot give you the precise proof, although I'm going to talk about a few words about this proof. But anyway, if we follow the proof very closely, then one can deduce this. So if we start from irreducible star representation pi, then what we get is an irreducible star representation of C naught to Q. And vice versa. If we start out from an irreducible star representation of C naught of GQ, then it extends to a CGQ, and it restricts, because core GQ is embedded into CGQ, it restricts to a irreducible star representation of core GQ. And in this way, we get this natural isomorphism between the two sets of equivalent classes of irreducible star representation of the two non-commutative spaces. Okay, this leads us to yes.
So in the previous slide,
Yes.
This whole GQ and C0 GQ inside CGQ.
Yes.
Can I compare them? Like, do you know one is bigger than the other?
Actually, that's a very good question. Yeah, but we can compare, but I think, yeah, it's a very, they are very disjoint from each other. Because, for example, in the classical case, let's look at the classical case, then polynomial algebra of SL2C, for example, it was generated by alpha, beta, and gamma, delta. And they are unbounded functions on SL2C, because SL2C is non-compact. But C naught SL2C, it consists of functions vanishing at infinity. So they are very bounded functions, but whereas these polynomials are very unbounded functions. So even though we can compare the two functions inside this common star algebra, it's my intuition that they are very disjoint from each other. Okay, thank you. But yeah, as a note, there is a actually, even though I didn't give you the definition of unbounded affiliated elements, actually from this, if we look at this definition, then one knows the concept of bounded transformation. So we can transform those unbounded functions, for example, alpha, into bounded functions vanishing at infinity and so on. So we can make some connections between the two by means of these bounded transformations, but purely as subsets, they are very much disjoint. Thank you. Any other questions?
Well, for this, we don't need a Harbin measure.
Oh, yeah, I think, let me see. Yeah, rather, I think Haar measure didn't come into the proof. Yeah, so yeah, rather than the quantum group structure, we just needed cis algebra structure. But occasionally we also needed some quantum group structures that we will see in the proof. But anyway, the proof was I would say more algebraic than analytic. So
Okay.
yeah, yes. Thank you. So other questions? Okay, thank you. Then before we get into the proof, I'm going to give you a brief look at the proof later, but before we get into the proof, let's look at a few important consequences of this universal property, this reinstatement of the universal property. Okay, so let's pick one irreducible star representation of PORGQ. Then one can conceive of this non-star preserving representation. Okay, so PORKQ was identified with the first tensor component inside PORGQ, which represented holomorphic polynomial. Okay, holomorphic polynomials in PORGQ, and classically, this first half of the map amounts to holomorphic extension of functions on KQ to the bigger space GQ. Classically speaking, holomorphic extension, and classically speaking, this pi, this representation pi means evaluation homomorphism at the point pi, because if we just let if we let Q equal to 1, then pole G becomes a commutative star algebra, and hence this corresponds to G exactly via pointwise multiplication. So this is the holomorphic extension followed by evaluation at one particular point inside GQ. That is the intuition, and hence we call this non-star preserving because this first embedding is non-star preserving. This non-star preserving representation of KQ in L of H is called the quantum holomorphic evaluation at pi, because this is precisely the Q-deformed analog of holomorphic evaluations of elements in pole K. Okay, from this viewpoint, this corollary, the corollary that we looked at here, this important corollary, can be interpreted as follows. So functions in pole KQ extend holomorphically to GQ because this, okay, the right-hand side set, the set of equivalence characteristics of irreducible star representations of C0 GQ. In fact, this can be interpreted as a non-commutative space. A non-commutative space underlying the C-star algebra C0 of GQ, especially from the theory of type 1 C-star algebra. And in fact, this is the type 1 C-star algebra. In type 1 C-star algebra theory, this set of equivalence classes of reducible star representation play an important role. For example, in planetary theorem, they appear as a space of integration of the any star representations of the type 1 C-star algebra C0 of GQ. So many such evidences indicate that this should be interpreted as a non-commutative space underlying C0 GQ. And because of this corollary, we see that this procedure of quantum holomorphic evaluation at pi can be considered as interpreted as like this, because this is given by non-commutative space representing C not GQ, which I just said that can be, but this is actually wrong, can be interpreted as a points, the set of points underlying the non-commuter space GQ, so that we see quantum Holomorphic evaluations are just point evaluations at the point, non-commutative points at GQ. And so this corollary actually implies, not implies, but can be interpreted as like this. And this recovers. I mean, this is the exact quantum analog of the classical phenomenon that polynomials on K, the smaller compact form, can be holomorphically extended to the bigger complexification G. Okay? So this is exactly that. And there is another very important consequence called the Iwasawa decomposition of the complex semisimple semisimple quantum group GQ. But to look at this Iwasawa decomposition, I should introduce some more preliminaries about this GQ. Okay, so we recorded this C naught GQ, even though we have proved the universal property, actually a priori is defined as the minimal tensor product between C of KQ and its dual C star of KQ. Hence, I'm not going to prove it, but the star algebra of unbounded elements affiliated to C naught of GQ can be given this because C star of KQ is actually given by this vanishing at infinity direction of the matrix algebras. Okay, so this irreducible KQ means the equivalence classes of irreducible representations of KQ. So that it is a co-representation of C of KQ, and because this is the discrete quantum group dual to C of KQ, one can prove that this is actually given by this, where n mu's denotes the dimensions of the finite dimensions of the irreducible co-representations of the quantum group D of KQ. Okay, so because of this, one can easily prove that actually this mysterious object of unbounded the algebra of unbounded elements can be given this interpretation. This is the direct product with this index sets, direct product of the matrix algebras with matrix entries taking its values in E of KQ. Okay. Yeah, you don't need to understand the precise forms of this, but I just wanted to give you the sense in which we are going to in which we obtain the Iwasawa decomposition. And there is a standard algebra homomorphisms from pole KQ into pole KQ star using the universal R matrices, universal R matrix. Okay, because pole KQ is a algebraic compact quantum group, it admits Peter-Weyl decomposition. And hence its dual is exactly given by this direct product of matrix algebra. So as an algebra, they are equal. So it's direct product. Okay, then I told you that this R matrices give rise to bilinear pairing between pole KQ by this formula. So if we just leave one argument as a blank, then this defines the linear functional on pole KQ, because if we put another element pole KQ here, then we get a complex number. Okay? And so we get two linear functions for each element inside pole KQ. And in this way, we define a map which can be checked to be an algebra homomorphism, plus minus. And then now we can interpret this holomorphic extension of the functions on KQ to functions on GQ by this. And also we can state the embedding of this polynomial algebra inside C of GQ. Yeah, in the universal property, I said there is this embedding, and this embedding was constructed by Hodges in the same paper, and the formula is exactly given by this, where the F sub 1 F2 is the Swidler notation. So you see, F1 is an element inside C of KQ, and M minus F2 is an element is a sequence of matrices. And hence, this defines on a well-defined element inside C of GQ. Okay, this is the sense which is involved in this embedding on torches. Then using this embedding, now I can state the Wada decomposition. Okay, so recall that the GQ is given by C of KQ tensor C star KQ, so that one can easily prove that this spectrum, instead of all irreducible star representations of C not GQ, can be described in terms of the spectra of C of KQ and C star of KQ. The correspondence being given by this, we pick an irreducible representation here and another irreducible representation of C star of KQ, and we send it to pi C tensor pi D. Okay, so that we get tensor product representation in the tensor product Hilbert space. Okay, so there is this very established natural isomorphism between the two spectra, between the two sets. Then, now, because of this consequence, which we obtain from the universal property, we see that if we just choose one non-commutative point inside GQ to define this holomorphic evaluation, then there exists two irreducible star representation inside using this correspondence here. Using this correspondence here, we get two irreducible star representations of C of KQ and C star of KQ respectively, such that pi is given by pi C tensor pi D. But then let's unravel the definition of theta pi. Okay, so we just looked at that the embedding, this embedding was given by F1 tensor L minus F2. So this is exactly F1 tensor L minus F2. But because this is given by pi C tensor pi D, we obtain pi C F1 tensor pi D L minus F2. Okay. Oh, I should have written down the tensor product here. Sorry. But now this U mu is a co-representation matrix corresponding to this index. So that U mu is actually a matrix given by matrix elements, which is an element inside and mu C A Q. Okay, and it is a fact that sorry, it gets messier. It is a fact that this co-multiplication applied to this particular matrix entry of the co-representation is given by so it's a kind of matrix multiplication like expression. So using these two, if we apply this theta pi U mu, which then what we would get is pi U mu 1 tensor L minus U mu 2 is exactly the right hand side. Exactly the right hand side, right? If we put tensor product in the middle. Okay. And this is the Iwasawa decomposition. Yeah, I'm going to explain why. This is a very vast generalization of the Iwasawa decomposition known only for SLQ2C. So, you classically, let's get back to the classical situation. Then mu, irreducible of KQ, corresponds to a unitary representation of K, unitary representation of K inside a finite dimensional vector space. Unitary representation, and U mu ij corresponds to matrix coefficients of this unitary representation E mu j, which is a continuous function and actually this matrix coefficient algebra. Okay, U mu ij, they are this, and so if we apply theta pi U mu classically, which corresponds to holomorphic evaluation, then this is just what we get is just a matrix realization. Matrix realization in the vector space in the vector space H nu. Okay, matrix realization because this amounts to point of complexification inside this. Okay, this theta pi u mu. The meaning of the theta pi u mu in the classical case is just the pointwise evaluation, so that classically u mu corresponds to pi mu x I j. Okay, so theta pi u mu is the matrix realization of the Lie group K. Okay, so this is the matrix realization to corresponding to this irreducible component of the compact semisimple Lie group K. And on the right hand side, you see this pi c is a point from KQ, whereas theta pi is a point of GQ, evaluation at GQ. This is the evaluation at KQ. Okay, and yeah, for this I cannot explain, but in the quantum group community, this is interpreted as the Q deformations of the AM part of the Iwasawa decomposition. Okay, so yeah, I cannot explain about this, but this is generally accepted in the community. So that this actually says that what this last equality means is exactly this GQ is given by KQ, A, and Q in the matrix realization corresponding to mu, because okay, so this is exactly the Iwasawa decomposition, and there is a remark. So this corollary was previously known only for SH2C. Oh, I forgot Q, and the fundamental representation of this. So that's where it was referred to as the Iwasawa decomposition of SH2C in this work of Poders and Voronowicz. So in this work of Poders and Voronowicz, they proved that for each irreducible star representation of a C node of SH2C, they proved this alpha, beta, gamma, delta is given by one irreducible representation. Okay, they didn't say irreducibility, but upon closely looking at their proofs, they only prove for irreducible representation. So, and irreducible representation of alpha, gamma star, alpha star, and another discrete component they denoted as this. They only prove this in their paper, but what we were able to prove is that we generalize this Iwasawa decomposition to most general case, to arbitrary complex semisimple Lie groups with arbitrary matrix realization, not just the fundamental matrix realization one. So this was the genuine quantum analog of the classical Iwasawa decomposition, and this Iwasawa decomposition that we found gives us a vast generalization, very vast generalization of this Iwasawa decomposition property. Okay, so let me finish with a brief look at the proof of the main result. So far, any other questions? Yeah. Yes.
So, well, I know the classical one of the cube, the Iwasawa decomposition, kind of splits out the semisimple and then solvable. So
yes,
it's also only true here because here, but
yeah, actually,
some semi-simplicity somewhere.
Yeah, that's a very good question, but I think I don't know very much about the interpretation of the second component as the ANQ component, but I think that's a worthwhile project to look at. Thank you very much for the suggestion. Anyway, this is exactly the compact part. Yeah, right. Yes. There's no other interpretation available for this, but to interpret the second component as ANQ, I think Voronowicz and Poders relied on this former property because the second component always is given by this form, AN and A inverse. Okay. They relied on this formal property, but yeah.
You can just take up the angle.
Yeah, yes.
You have this A.
Yes, exactly.
And then you prove the other guy is no.
Yeah. Yeah. But now they are all operators, non-commuting operators. That's an interesting part.
Yeah.
Okay, so let me give you a few words about the proof. Okay, I will be very sketchy because the proof is very long and I cannot cover it in the limited time. So again, record the algebra homomorphisms and this description of C of GQ. Then yeah, here is the embedding given by Hodges. So in the universal property, this time embedding of Paul GQ into C of GQ was built in, but it was we didn't have to prove it because in this paper already this algebra embedding was constructed. Okay, Paul GQ is embedded into CGQ via this formula, where F is sent to F1 and L minus F2, and G is sent to G1 and L plus G2, and they are multiplied the component-wise multiplication. And let's take a unitary irreducible star representation for GQ into L of A. Let's take any such irreducible star representation. Then we want to show this. Actually, yeah, even though I stated the Iwasawa decomposition as the corollary of our main result, actually the proof goes the reverse way, the reverse direction. So we actually proved the Iwasawa decomposition, and using the Iwasawa decomposition, we were able to prove the universal property. Okay, we want to show that this pi is actually given by pi c tensor pi d, followed by iota, this embedding of Paul GQ, because now then so then we can prove that this representation of Paul GQ extends to C of GQ. That is what we are looking at. Well, that is what we are looking for, because in the universal property, yeah, we were seeking to find this extension of the irreducible star representation to this bigger space. So actually, we are seeking this pi c and pi d such that pi is given by pi c tensor pi d followed by the embedding iota. Okay, for some pi c in the spectrum of C of KQ and pi d in the spectrum of C star of KQ. For that, we follow the usual method to obtain the classical Iwasawa decomposition in classical complex semisimple groups. So remember, this is theta pi u mu. Okay, this is theta pi u mu star. Holomorphic evaluations, and I told you that this classically corresponds to this matrix realization. And to get the Iwasawa decomposition, we first form the square of the matrix realization, and then then classically, okay, let's proceed step by step. We form this positive invertible operator, and we decompose it into some other matrix such that A is given by upper triangular matrix such that whose diagonal entries are positive. Okay, we can do this. We can do this using a decomposition called Shortsky's decomposition. This isn't very well known from the analysis community, but anyway, we can apply the Shortsky's decomposition to obtain this upper triangular matrix with strictly positive diagonal entries, and then using this, we proceed. We compute this, and then by definition, this matrix is unitary because they are same, they are equal. And if we take the inverse from the right on pi mu x, then what we would get is an invertible matrix. And this way, this pi mu x and pi c x A inverse. Okay, let's say U. This U A, we obtain this, and this is the Iwasawa decomposition. This corresponds to K, a compact part. This corresponds to AM part. Okay, this is exactly what we apply to this quantum situation. So Shortsky's decomposition apply very well to operators on Hilbert spaces, and hence we just forget about this classical procedure, but we can obtain from this we obtain an upper triangular matrix with diagonal entries consisting of invertible positive operators on H, and from there, and here I denoted that by this pi d. From there, we can proceed to obtain this unitary part, and let's go step by step. So first observation to be made is that this square matrix doesn't depend on the first tensor component of C of KQ. Remember this, so that this one is actually independent of the first tensor component, and hence they are purely numerical matrices. Okay? Numerical matrices, and using this decomposition into numerical matrices, we can construct a particular star representation from the discrete part into the same Hilbert space, such that we obtain this Shortsky decomposition of the positive, therefore, this invertible positive matrix inside NM mu of H. Okay, this is the upper triangular matrix, and hence we get this unitary part by means of taking the inverse from the right on this in this quantum holomorphic evaluation. Okay, just like in the classical case, and this is well defined because this U mu matrix entries of those co-representations form a well-defined basis of core of KQ. This is well defined, and this is unitary because of this relation. They are unitary, and one proceeds to prove that pi c is actually a star representation, and also prove that for elementary tensors inside C naught of GQ, pi c, pi d, that is images of pi c and pi d, they commute with each other. Okay, such that, so this commuting property means that if we define pi c tensor pi d by pi cf pi d x, then this becomes an algebra homomorphism, and one can check that it becomes a star representation. So we obtain an extension of star representation to, this isn't the extension. Anyway, we obtained a star representation of C naught of GQ in the same Hilbert space. Then one can prove that this is actually irreducible, and it extends to the bigger star algebra C of GQ. And from there, one also proves this. One can prove that pi is given by pi c tensor pi d iota. Okay, I've been very, very brief because those involved in the proof are quite complicated to describe in very simple terms. I just wanted to give you some steps and ideas behind the proof. So we proceeded just like in the classical case. We decomposed this square of the holomorphic evaluation into upper triangular matrix and the unitary matrix, and from there we proceeded to prove the commutativity of the two representations, and hence we defined the representation of C naught of GQ in the Hilbert space by means of this formula. And then we proved the reducibility and the restriction property. And in this way, we obtained the universal property of C naught of GQ. I'm sorry, yeah, I think the proof parts have been very, very briefer, and I need to correct some. But anyway, thank you very much for your attention.
It's a very nice talk and we have a lot of results.
Yeah.
Any question?
Yes.
Just clarify your definition by universal property.
Yeah.
I mean, with the previous definition of minimal tensor product.
Yes.
So they are less equivalent.
Yeah, actually, the equivalence was proved for SLQ2C in the original paper written by Poders and Borovitz. But after that paper, the universal property has been lost from the literature. No one has ever talked about that. But what we proved is that actually this quantum double, the quantum double has been taken as the definition of Q-deformed complex semi-simple Lie groups after this work of Podolsky and Voronowicz. But what we proved is that this quantum double is actually equivalent to the universal system algebra satisfying the universal property that I laid out in this. So they are equivalent.
And you said this definition by minimal first of all for quantum double, it's not Q. You said that a question, where is the universal property? What do you mean it's not universal?
Okay. So actually that is the starting point of our research. So So in our story, we said that originally the scheme of executivity was defined in terms of as a universal system algebra satisfying this property, and they proved that this is actually equivalent to this minimal tensor product. But after that, these Q-deformed complex semi-simple groups are always defined as this, but not as universal system algebra.
So this, in what sense this is not universal?
No one has known. No one has known if this is a universal system algebra or not. But we recently proved that this is actually a universal system algebra.
What do you mean by universal system?
Satisfying this universal property. They satisfy this universal property. Okay. In this precise term. So the universal property has been lost, but we just recovered it to every complex simple. Any other question?
So can I understand the maps that you define for I plus minus?
I plus minus?
Not here, but later.
L function.
Oh, L.
Yeah.
Okay.
Yeah.
So this L, I wonder, can I understand this as some kind of like quantum Fourier transform?
I think that's quite that's different. They live in a different realm. I think the Fourier transform uses the half state, but it never uses half state. The Fourier transform is in its origin, it's an analytical object, but it's purely algebraic. It is only defined in terms of the universal matrix. Yeah. So they are different. I'm not sure if there is a connection, though. I don't know.
You are using some kind of pairing here.
Yes.
Bracket here.
Yes.
So if I do have a hard state, and I use the hard state to define that pair, then maybe there's some.
Yeah, it should be Fourier transform.
Yeah, of course. But yeah, this actually, let me reveal the identity of this universal array. So actually, there is a standard pairing between these two objects. This is very, very low, and actually this amounts to differential pairings between Lie algebras and smooth functions. Okay, and even in the Q-deformed realm, this Q pairing persists, and this universal I matrix is actually a kind of object living in, not exactly, but an algebraic completion of this tensor product of UQ of UQG tensor UQ of G. And because of this, it admits a pairing between 4KQ tensor 4KQ. Because now its tensor component can be paired, right? Because of this, we get this pairing between R and two elements in leading in 4KQ. So they are very much algebraic, and because this pairing between UQ of G and 4KQ, they don't involve any mention of hard state. I think we don't need hard state, but I think it would be an interesting project to find a connection between the hard state and pairing between UQ of G and 4KQ.
So a follow-up question is that the quantum Fourier transform or this notion of some notion of pairing that you can get. It's very important for holomorphic quantization. If you want to construct like some kind of TQFT.
Yes.
Yeah, so it seems that this allows me to do holomorphic quantization for SL2C transcendence.
Ah,
Have you?
no, I haven't looked at it, but yeah, that's very, very interesting. Yes,
Yeah.
yes, indeed. Because yeah, this pairing, even though it can be described in algebraic terms, they are very much geometric. They have a geometric origin. I think, yeah, that's a very profound. That would be a very profound connection if we find some. Thank you.
Yeah.
Any other questions or comments?
Then pose no question. Let's thank Professor Lee again.
Thank you. Thank you very much.
This is the end of this